All right. So picking up where we left off last time, we're going to look at the math and the picture, the diagram for multi-level cache. So the first thing to add to his word description here is a little picture so that we're clear on something that in the processor, we have an I cache and a D cache, and those are separate. Remember that they're at different points in the pipeline, right? We read the I cache in the first stage of the pipeline, and then we read the D cache or write it in the fourth stage of our 5-stage pipeline. So there's two separate caches, the I cache and the data cache. And that's again here what he calls the primary cache. And remember, primary could also be called L1. So we have an L1I and an L1D. And then he talks about the level 2 cache, and he switches nomenclature here from the primary to level 2. So to put it back in the other nomenclature, it's also called the secondary. And then the important thing to note here about the secondary is that it's a joint cache, meaning that its services misses from both the I and the D. So it has I and D in it. So both instructions and data are in the L2 cache. And again, so it's a joint meaning combined. These words mean the same thing, joint, combined. I and D. And then just to extend the picture, if there's an L3 cache, which we will have, the L3 cache is also I and D or joint. So all caches past the first level, all the caches in remaining levels, L2, L3, always contain both instructions and data. It's only the initial primary or L1 cache that where there's separate instruction and data. And so that will be noted in our formula. That'll have an impact on our formula. Okay, so here's the simple math. So this time we're going to start out with a base CPI of 1. So maybe we have a dual issue machine now to get to a base CPI of 1. And then a little trickiness here. Note that he gives us the clock rate and he gives us the memory access time. And so we're going to take these two things and from them, we're going to compute how many cycles it takes to get to memory, because again, we're computing cycles per instruction. So we need everything to be in cycles. This 100 nanoseconds, we have to convert that to cycles. So he does that here with a little bit of dimensional analysis. He says 100 nanoseconds times 0.25 nanoseconds, and 0.25 nanoseconds is just the reciprocal, right, of the 4 gigahertz. So that's 250 picoseconds converted to 0.25 nanoseconds, right? So just nanoseconds versus picoseconds, and he does that, right, because he has the access time in nanoseconds. So we need all the things to be in the same time scale. And so anyway, you just do that little bit of math there, and you get that the access time in cycles is 400. And he says, okay, with just the primary cache, he computes what our CPI is going to be. And note that he's already computed what I called last time, the per instruction miss rate. So he already computed that for us. He gave it to us. Now, again, normally we're going to have to, compute that for ourselves, given the I miss rate. And the D cache miss rate. So normally we're given those two things, and the percentage of loads and stores. Remember, those are the three things that we need to compute the per instruction miss rate. Here he gave it to us, but we need to be able to be prepared always to compute it ourselves. But having given it to us, he just plugs it into the equation here. 0.02, that's the 2%, 0.02 times the number of cycles. And lo and behold, 400 times 0.02 is equal to 8. So this is equal to 1 plus 8 equals 9. So you can see immediately how enormously horrible that is. And of course, one of the reasons is because he's got a realistic number of cycles here. He said, hey, the memory access time is 100 nanoseconds, which is, about right. And I've got a really fast processor, 4 gigahertz, and that means that the number of cycles out to main memory is this enormous number here of 400. Okay. So then he says, all right, so let's add a level 2 cache. And this time he says, okay, the access time is now 5 nanoseconds. And so he does, again, the same math, 5 nanoseconds divided by 0.25 nanoseconds is equal now to 20 cycles. So recall that the access time to main memory from the previous slide was 400 cycles, right? So you can see now why we have caches on our processors and why we have multiple levels, because 20 is a decimal order of magnitude plus a factor of 2 smaller than 400. And 20 is a very reasonable number. If you work very hard, you can push this number down to less than 10. And that's a very reasonable and very good thing to do. So you can bring it down another factor of 2. Okay, so then he puts it all together. So now we get, so recall from our picture now that here's our base CPI, and our per instruction miss rate already given to us is the 0.02. And now that 0.02 now gets multiplied instead of by 400 by 20, because this is the miss rate out of the I and D caches, and now the miss penalty from there is 20. And then we've got a much larger L2 cache. And with the much larger L2 cache, we have a much smaller miss rate out of the L2. And so here you see the magic trick that we're playing. There's always magic going on. Here's the magic going on here. We're taking this ginormous number 400, and now instead of multiplying it by 0.02, which we did on the previous slide, we're now multiplying it by 0.005. So you can imagine that's going to make a very large difference, because that's a factor of from 0.02 to 0.005. You know, that's a factor of something smaller, right? Factor of what? 4x. Anyway, so now you multiply all this mess out, and instead of 9, we get to 3.4. Well, 3.4 is not great, but it's a whole lot better than 9. And so then he computes his standard, you know, performance ratio. Remember, performance ratio is always computed big number over small number. And he says, okay, the new system is 2.6 times better than the old system. So that's pretty good. But it's not great. It's not great. So next, we're just going to do this one more time, and we don't have a slide for this, but let's just do it because that's what we're going to want to do. We'll just use his same numbers. Let's actually we have space for it. We can do it without going to another slide. We'll just make space here. So with L2 and L3, the equation will be 1, there's the 1, plus 0.02 times 20 times 20. So that's the L1 to L2 miss penalty, 20 cycles. And now we're going to put a L3 in there. And we need now a new number, right? Here, this was the L2 miss rate. Now we need an L3 miss rate. And let's just assume that it goes down from 0.5. That when we put on a cache that's 10 times bigger, and typically each level of cache is somewhere between 4 times bigger than the previous cache and 10 times bigger, somewhere in that range. So let's assume that in this case the next level is just we'll just say nominal is just 4 times bigger than the L2. So our L3 is 4 times bigger than the L2, because that's kind of as small as you'd want to make it. So we'll get a conservative result here. And when you multiply the size of the cache by a factor of 4, you can expect the miss rate to go down by about a factor of 4. That's just what you would intuitively expect. And of course, you're going to run simulations to prove this, but let's just assume that for a moment. So this number goes from 0.5% to 0.5 times 0.5 divided by 4%. And so that goes into our equation here as 0.005. So that's this number still, 0.005 times, and now this is our miss rate to the L3. So as long as we're still on this, as long as we're still on the chip, the miss rate between one level of cache and the next level of cache will always be a number that's, typically like about this size, 20. Or again, if we work really hard, we could get it down to 10, but let's just assume it's 20 again. So this is L1 to L2, L1 to L2. This is L2 to L3. And we're going to assume that that number is still 20. So see, we still use the 0.005 because that's the miss rate out of the L2, but the miss penalty out of the L3 isn't the 400 anymore because we're not going off chip. We're going to the L3 cache. And so that miss penalty is 20. And then finally, we go out to main memory. And now our miss penalty is our 0.005 divided by 4 plus 0.005 divided by 4 times the 400. And so now we want to do all that math and come out with a new number here. So this number here, 0.02 times 20, is 0.4. So this is 0.4. And 0.005 times 20, this number here, 0.005 times 20, is going to be what? 0.01. What is that number? Let's get the calculator here. Where is it? Right, there it is. 0.005 times 20. Make sure we don't make any mistakes here. That's 0.1. So that's 0.1. And then finally, the 4s here cancel. So we get 0.005 times 100 times 100. And 0.005 times 100 is pretty straightforward. We just move over the decimal point two places. So we get 0.5. So this number is 0.5. And so we add these numbers up now and we get 1 plus 0.4 plus 0.1 plus 0.5. So we get 2. Let's see. 1 plus 0.4 plus 0.1 plus 0.5 equals 1 equals 2. So now we've gone from 3.4 by adding a level 3 cache. We've gone from 3.4 down to 2. So we've improved it by another factor of, almost 2. And so relative to the primary cache only system, we now have 9 over 2, which equals whatever 9 over 2 equals. What is that, 4.5? So now we've improved the performance by a factor of 4.5 over the primary. And we've got the CPI down now to a very respectable 2. So we started out with 1 and we only raised it by 1 with all of the cache misses in the system. So one thing we should take away from this is again, working really, really hard by putting an L1 cache, an L2 cache, an L3 cache. So we're clearly doing a lot of work here. We're spinning a lot of memory bits. And we're doing it because if we don't, the CPI we started with becomes enormous, and we might as well not have pipelined the processor to start with. And we want to make the processor run almost as fast as if it was fully pipelined and there was no cache misses. So clearly what we need to do here is we can improve this by a lot by saying that instead of using the smallest additional factor of size in the L3 cache, which we used was 4, we said we just made it 4 times bigger. We should make it 8 times bigger. And if instead of 4 times bigger, we make it 8 times bigger, then this 0.5 here, this 0.5 would become 0.25. It would go down by another factor of 2. 0.25. It's hard to read. And anyway, our CPI then would get down to 1 point. Let's see, 0.25 plus 1 is 0.4, 0.5. So 0.75. So we get down to 1.75. And so now, we're getting more and more respectable each time. 1.75. And our biggest factor now is back to our primary cache. If we make this number here 0.25 by making the L3 8 times bigger than the L2, a much more reasonable thing to do. If you're going to bother to put an L3 down there, you might as well make it big. And we're now back to it's the primary cache to L2. The primary to secondary cache that has the biggest impact. And so now this is where we said, okay, this number 20 here, if we work a lot harder, and it's well worth the work to do it, we could push that 20 down to 10. Let's just say we make it 10. If we make it 10, then this 0.4 goes to 0.2. And now we're in great shape. Now we get 0.25 plus 0.2 is 0.45 plus 0.1 is 0.55. Now we've got a CPI of basically 1.5. And that's really excellent. That's where you really want to end up. You want to increase the CPI by only about half what your base CPI is. And you can say that I then have an excellent result. So it can be done. And it's all about just how much memory you throw at it. And so again, just recall what we said, that when we build a processor, that the processor looks like this. This is the takeaway here. The processor looks like this. Chapters 1 through 4 look like this. 1 through 4. Chapters 1 through 4. And then we put the I and the D cache around it. And then we put the level 2 cache around it. And then we put the level 3 cache around it. And this is what our processor looks like. And you can see that it's 90% memory. So if you want a really, really fast processor, when you look at it, you're going to look at it and it's going to look like basically a memory chip with a tiny little thing in the middle of it that's the processor. And that's because of the math that we just did in the last 2 slides. If we don't put down a big enough cache, and if we don't work and make the miss rates between those, the miss latency, the time to get from one layer to the next, if we don't get that number to be small, then we're not going to be able to get to the CPI that we want to get to. Okay. So this just means, this means, got to happen in one cycle. You only get one cycle, to access the cache, because that's what the pipeline is set that way. And so you've got to do it in one cycle. And then the L2 and the L3, And the L4, it's all the same time. You need a low miss rate. Low miss rate. And that's only half the story. And a low miss penalty. So the low miss rate comes from size. Got to make it big. And the low miss penalty comes from, has to be integrated. That means, integrated means on the same silicon. On the same silicon. So the processor and the caches all have to be this monolithic piece of silicon with a lot of wires going back and forth between them. And these are just not really the results. The results are what we just said here. We need to be big and we need to be low latency. Big and low latency. This is all crap. So the only takeaway we want to say about that when you build, recall this term out of order, that when we build a processor that can execute instructions out of order, that what you can do is you can make the primary hit rate, that thing that he talked about on the previous slide, you can then not have to access the primary within a single cycle. Because while you're waiting to access the primary, you can look around and try to find some other instructions to do. And the advantage of this is you can make the primary, the L1 D cache, bigger. And if you make it bigger, you can lower the miss rate. And so this is the mentality of people that design out of order processors, is they make the L1 D cache bigger and they don't try to access it in one cycle, as he said that you need to do on the previous slide, because you can find other things to do while you're waiting to do that access. But we know as now experienced CPU designers that this doesn't work very well. And it doesn't work very well because there isn't that many things you can find to do. And we know that because we've looked at programs, we've written programs and we've looked at programs, and we see that the way they work is that they do something, they load something, and then they use it. And they load something and they use it. And so it's difficult to find other things to do. And you can find a few, but you can't find a lot. So you have to be very, very careful about assuming that you can find enough things to do to allow you to push the to push out the L1 access time. And this part here is just garbage. This is nonsense. It has nothing to do with executing under the cache miss. It's executing under the fact that you made the hit time longer. And he clearly doesn't understand that. Anyway. The algorithm that you used for a program, can always affect the performance, but that's the purpose of the benchmark suite, right? The reason we have a benchmark suite, a whole set of programs, 20 odd programs, is because programs are different and algorithms are different, and they all have slightly different characteristics. So we design our processor so that it works the best on all 20 of these programs. We can't just design it for one. You got to run all 20 of them and see what design gives you the best result, on average over all of them. Because of this, because what happens is very dependent on the program and the algorithm. So we have to pick 20 representative programs, 20 or more, and that's how we design the processor to make it do the best on all of those. You can't just pick one. All right. So we're going to think about caches a little bit differently now. And this will be the subject of our next lab. And so what we're going to do is we're going to talk about blocking. And so let's figure out, first of all, what that means. So we'll leave his picture here for a moment and try to get into our head what it is we're even talking about here. Hello, that's not right. Don't do that to me. Where is the... Oh, I got a problem. All right, so we know now how to multiply two matrices, right? When we multiply two matrices, A times B equals C. We know that C11 here, that we take this row times this column. So we call this little a and this little b, that C11 equals A dot B, right? It's the so-called dot product or inner product of A and B, right? You multiply each of the individual elements and then you sum them up. That's what our matrix multiply routine does. Now here's the problem that we have the matrix. A matrix is a two-dimensional thing, right? 2 dimensions. But memory is 1 dimensional. And that means, and we can talk about storage of matrices, and you can store matrices in what's called row major order or column major. So row major or column major order. And row major order means that if we take A and we call it A1, A2, A3, A4, the rows here, that those rows are stored in memory as A1, A2, A3, and A4. So it stores them, linearly like that. Column major order would just do the opposite, right? It would just store them, the columns, linearly. Here we're storing the rows in line. And so here's the problem. The problem is you can see that as we access the elements of A, say there's 4 of them here, that you can see that they will come sequentially in memory. So it's quite easy to access them. And we can get 4 at a time, for example, because they have what? They have spatial locality. They have excellent spatial locality, these 4 elements that we need, that we're to multiply this row times this column. Getting the elements of this row is very easy. They have great spatial locality. We can grab the first one and we can get, all 3 of the other ones all at the same time. But B is stored in memory the same way, right? Matrices, all the matrices will be stored the same way, either row major or column major, because you don't know which way you're going to multiply them or how you're going to multiply them. So you just have to choose one way or the other. And so that means that all the elements of B here that we need in order to perform this dot product aren't going to be like this. So the rows of B, if B looks like this, B1, B2, B3, B4, B1, B2, B3, again, so they're both stored in row major order. We can see that the elements of B that we need is this one, and this one, and this one, and this one. So that's really bad news, right? That's really ugly. So because there's no way that they have no spatial locality at all. And so when we go to get them from memory, it's going to be very, very inefficient to get them. And in fact, what will happen as you get them, since they're not right next to each other in memory, it's easy for them to collide in the cache. It's easy for them to end up on top of one another. And so if they end up on top of one another, not only take you a long time to get them, but once you get one of them one time, you then throw it away when you get the next one. It's possible that those 2 things will collide. Those 2 lines will collide in the cache, and you'll have to throw the previous line out. So it won't even be in the cache anymore. And if that happens, of course, the advantage of having a cache has gone away. So that's all bad. Okay, so what do we want to do? Is we're going to say, okay, well, here's a magic trick. That if I want to multiply these 2 matrices and get a 3rd matrix as the result, that it turns out that I can do this to the matrices. This is called blocking. And so I can call this, so if this is A and this is B and this is C, I can call this A11 and A12 and A21 and A22, and so forth with the B's, B11, B22, B12, B21, and similarly with the C's, C11, C22, and so on. And so it turns out that C11 is equal to A11 times B11 plus, A11 times B11, A11 times B11 plus A12 times B21. And again, and all these capital letters, all these caps, capital letter equals matrix. So these multiplications here are matrix multiplications, right? So when we say A11 times B11, that in and of itself is a matrix multiply, just like the earlier matrix multiply we talked about. So if these are all 4x4s, then these individual ones here are 2x2s. And so this is a matrix multiply, right? Where you've got rows that are 2 long and columns that are 2 long. And so the trick here, or the magic is that when you block it like this, that you get smaller number of elements that you need to get into your cache at any one time. You can see that we're doing multiply here by smaller matrices, and that means that there's less items to go into your cache, and so they're more likely to fit in the cache. And so when you do the lab, when you block the matrix, as the algorithm that we'll go back to in a minute here shows how to do, when you block the matrix multiply, when you run it, when you want to try and see how blocking helps, you got to make sure that you start with small enough cache sizes so that originally the elements don't fit in it. And as you make the cache bigger, you will see that the elements will, when you start out with the matrix multiply unblocked with that size, and then you block the matrix multiply with the same size caches, you'll see the performance go up. So that the key is that you have to make sure that you find the right size caches to start with, where the original matrix multiply unblocked doesn't fit, and that after you block it so that you have a much smaller number of items that you need to get to fit into the cache, that it will fit, and so the cache performance will be better, meaning that as measured by the hit rate. And we'll show next Tuesday we'll bring up Mars and show how to use the actual hit rate measurement portion of the program. You can find it just by looking in help, but I'll bring it up and show it. But that's what we'll do in the next lab, is we're gonna block the matrix multiply so that it looks just like this. And then we're going to measure the performance and see that the performance improves when you make when the number of elements that has to go into the cache at any one time will fit in the cache versus not fitting in the cache. All right. So here's the, here's the alphabet soup. Oops, oh, don't do that. So here's the alphabet soup version of the program. And they don't give it to you in actual MIPS instructions, but you can see what they're doing. They just again, they're doing exactly what the picture shows. They just make the matrix multiply get done in smaller blocks. And then after you do the smaller blocks, then you just you just do a dot, just do the same dot product except that the elements of the dot product are matrices instead of individual elements, just like the picture showed. And here he shows, okay, what happens, the access pattern when you do this, and why you win. But it's clear that the reason you win is just because you have a smaller number of elements, and therefore you can keep the elements that you want in the cache, and they'll be there when you need them, rather than having gotten thrown away because you're doing a matrix multiply that's so big that the elements won't fit in the cache. They just thrash each other. And you can see the beauty of the algorithm. He measures it here for you nicely, and he shows that, wow, even as the cache size gets big, even as the matrix size gets bigger and bigger, the performance stays flat versus this curve here, which shows that, with a fixed cache size, that as he was increasing the size of the matrices, that the program performance just drops, straight down. It just drops straight down because the matrix just won't fit in the cache anymore. And as soon as he blocks it, he gets a nice flat, response, no matter what the size of the cache is. So blocking really works. It works quite well, as you can see, just flattens that curve right out. Okay, so again, because of the author's philosophy here, he sticks this dependability stuff, kind of right here in the middle to make sure that we talked about it, and we will. And the important thing, and you'll all have heard this term, is this, there's all kinds of alphabet soup on this page here, but we'll just focus on this one, the mean time to failure. All these other ones are just closely related to mean time to failure. It just says, okay, on average, how long is it going to take for something to fail? And you can do simple math here. And the best example are disks. In the old days, the best example for a computer would have been, vacuum tubes. But for us now, the best example is disks, because disks are the things that are mechanical. They're not completely electronic. And so disks are the things that fail the most often. And the key point here is that the disk manufacturer is going to tell you that the mean time to failure is equal to, a million hours. And that's like, I don't know, 10 years or something like that, approximately, I think. So you would reach the conclusion then that, okay, that's a long time. I don't have to worry about disks failing. But that's the mean time to failure. And so when you want to really compute what's your time to failure, you have to take the number of disks you have and multiply it by this number to get the actual failure rate. And you can do that math, and you'll get an opportunity to do that math, on a quiz. And it's very simple. You just use some simple dimensional analysis, and it'll work out. Very simple. And what your conclusion is going to be is that, oh my goodness, I'm not going to get a failure every 10 years. If I have 1 million disks, which is not very many these days. I mean, there's billions of disks out there, not millions of them. And there's, another million being built every day. Got to have some place to put all those cat photos. And so they're all, so if you have a data center and you want to figure out, what is your failure rate, you're going to be multiplying those two numbers together. And that's going to tell you how often a disk will actually fail. And when you do that math, you're going to be astonished. You will be astonished at the result. So the key point is that, you've got to look at not just the failure rate, but you got to look at how many of them you have. That's the takeaway here. Okay, so just like we did with the two's complement number system, we're going to come back to this Hamming code after we do the next two sections here. And he stuck it in the middle here because he wanted to make sure that we did it, but he didn't need to do that for me, because this redundancy, this coding is incredibly important, and so we would not have neglected it anyway. And I've mentioned this before, that in today's technology, if you try to build a computer that never fails, that it will be 100 times bigger, burn 100 times more power, and therefore you would never be able to carry it around in your hand like you do. And so we don't do that. We just assume that we're going to get these failures due to things that we'll talk about, and then we're just going to fix them. So we have to use coding to do that, and we'll talk about how that works. We'll come back to that. So instead, we're going to stick with memory here. Or with the conceptual parts of memory, and then we'll come back to that physical part of memory, which is the thing we have to fix with the encoding. So in the last number of years, this concept of virtual machines has become really important. Now the concept of virtual machines has been around for a long time, back to the 1970s, but it didn't become really important until this company VMware came along, because VMware recognized that computers had become so pervasive, and there were so many of them, and they were computers were growing in the world at an exponential rate, just straight off the chart. That they said, wow, we got a real problem here, because these computers, as they were growing from generation to generation, that they weren't compatible with the previous generation. And the reason for that was because sometimes the hardware wasn't compatible, sometimes the software wasn't compatible. They would release different hardware with different software, and just, the whole thing started to become a mess. And so what happened was you saw large companies that had a data center, because they needed a ton of computers to run their business. And it turns out, however, that they didn't have just enough computers to run their current business. They had to have a whole bunch of computers that ran their software for their business from 5 years ago, a whole bunch of computers that ran the software, because our friends Microsoft would release a new operating system, every 2 years. So, and the hardware people would release new hardware every approximately 2 years. So between the hardware and the software continuing to get released, they were having to have multiple sets of machines in their data center to run all of this old software. And they couldn't, and they had databases that were compatible with that version of the software. And if they tried to move that database to a new version of the software, it would turn out it didn't work. Or if they tried to move the whole thing to a new piece of hardware, it turned out it didn't work. And the problem was that the computer vendors, here's the real issue, the hardware vendors at the time, like Hewlett Packard and IBM, and the software vendors at the time, Microsoft and well, that was pretty much only Microsoft at the time. So those folks, they had no reason to make this not happen, because they wanted to sell you more software. They wanted to sell you more hardware. And so they didn't have any impetus to make all their other stuff compatible. They wanted you to buy as much new stuff as possible, as many new software licenses and as many new, instances of hardware as they could possibly get you to buy. That was their business. So VMware saw this, and they saw, huge opportunity. Whenever there's a huge opportunity, the venture capitalist will fund you to exploit that opportunity. So VMware said, hey, we're going to come in, we're going to solve that problem that the big guys, Microsoft and Hewlett Packard and IBM, that you don't care about. And so there was a bunch of money available there if they could solve the problem, and that's what they did. So basically, a virtual machine is just a piece of software. They wrote a piece of software. Let's see if we have a picture here. No, we don't have a picture. They wrote a piece of software. If this is the software stack, here's Microsoft. So here's Windows. And Windows ran on top of Intel. This was the so-called Wintel monopoly. And that was really the problem. And so VMware came in and they put another piece of software in between Windows and Intel. And that's generically called a hypervisor. And specifically, VMware calls it, their what do they call it? Machine monitor or something. But the generic name is a hypervisor. And really, so Windows is, big, bloated OS. And their whole goal is to keep it a big bloated OS so that, it looks like, they're bringing real value. And VMware put in this thing called a microkernel. So a tiny little operating system that just did the bare minimum of stuff required, that you could make it compatible between, all the hardware and all the software above it. So basically it was a compatibility layer that they installed between Windows and the hardware, so that any piece of hardware, that you got would run any old piece of software that you had. And the way they did that was and then of course on top of Windows here is the apps. And so once they stuck this micro OS in here, then all of this stuff here, the apps in the old Windows OS, this would get compiled together as an app. So it would no longer have operating system privileges. So they literally compiled the Windows operating system and the app, those two things that you wanted, that you bought the app at the window and that version of Windows at the same time, and you made your business run with that software. And so they take that app and that version of the app and that version of the OS, and they compile it together because they know it works together. And then it runs on top of this micro OS, which allows you to put it on any piece of hardware. So this is, as you can imagine, if you could do this, and they did it by spending, many engineers and many millions of dollars. They made this work, and as a result of making this work, they this is a many billion-dollar company, many billion dollars company, enormous company that became enormously successful by exploiting this nightmare that the Wintel monopoly actively kept going. I mean, they actively tried to make this as hard on everyone as possible, so that they would have to keep buying more copies of new Windows and more copies of new hardware. Anyway, so that's what virtual machines are all about: being able to run any old OS and any old app on top of any piece of hardware by putting in a microkernel that does just the absolute minimum amount required to make those things work together. And the author talks about, he's going to give us an example here in a minute. But basically what happens, right, is that the old operating system, when it tries to do something that it thought it had the privilege to do, that now takes an exception, and which means it can't do it. And the reason it takes an exception is because now that piece of software is not running in the operating system mode anymore. It's running in the user mode. So processors all have user mode and supervisor or operating system mode, and for all the code that's running in the user mode, if it tries to access like the disk, it's not allowed to do that. And so anytime it tried to do that, it would cause an exception, and that's where the virtual machine monitor, that's where the hypervisor steps in and does it instead. And so that's how it forces this or makes it so that it can be compatible. It gets in there, gets in the way, or gets between those two things. So as it says here, the virtual machine manager actually handles the real the real IO devices, and the old operating system, Windows, doesn't get to talk to the IO devices. And IO devices are an interesting case, but it'll turn out here that the most important case isn't mentioned here in the slides, but we'll generate our own slide and talk about what the actual most important case is. And we'll come back to that in a moment. Here's his incredibly simple, trivial case, is just virtualizing the timer. So one thing that you might just doesn't seem that important, and it's not, is just keeping track of time. And when the operating system wants to start wants to change context, it'll wait for the timer interrupt to go off, and now the timer interrupt can't be serviced by the old OS, so it has to be serviced by the virtual machine monitor. So the virtual machine has to do that. So VMM emulates a virtual timer. Anyway, this is a case, but it's not the really important case, and we'll come back to the really important case in a moment. It's right after we talk about the next virtual thing. So we just finished talking about the virtual machines, and now we're going to talk about a different kind of virtual. And and then we'll come back and talk about the important case that of what the virtual machine monitor or the hypervisor has to do. So here's the other term, virtual, and it's unfortunate. It's really quite unfortunate that we use this term virtual so close together with two things that we just talked about, the virtual machine monitor, and now we're going to talk about virtual memory. And those two things, even though they both have the word virtual in them, are completely orthogonal things. And so the first thing we have to do is make sure we're not confused, that we're going to come back to it because of a related issue, but we're now done with virtual machines. We're now moving on, and we're going to talk about virtual memory, and that's completely different thing. So that's the first thing we need to make sure that is in our head, that virtual memory is a completely different thing than virtual machines. So given that, what is virtual memory? So let's just talk a little history for the moment. So the term virtual memory originally came from the fact that memory used to be incredibly expensive, and it was incredibly expensive to have very much of it. And programmers, when they write programs, you never want to tell a programmer who's trying to write a very good, correct program, you never want to tell him that at the same time, oh, you need to make the program, and the data structure is absolutely small as possible. You never want to tell him that, because if a programmer is both trying to write a program that's completely correct, and he's also at the same time trying to jam it into some, artificial, size, that the likelihood of it being completely correct when he's done goes exponentially down. So you want to tell the programmer that when he's writing a program that he has infinite space and infinite, number of instructions, that everything is infinite. What he needs to just concentrate on is writing a perfectly correct program. So we have the concept then of what's called virtual memory space. And virtual memory space is, if you will, it's infinite. The programmer just assumes that he has infinite space, infinite memory storage, infinite storage for its instructions. Everything's infinite. And to try to make it, or to try to get the hardware to look like that, what they created was this virtual memory concept, which means that what happened is when this program ran, when the programmer's nice, well-constructed program ran, that it used way more memory than was actually available on the processor. And so it was constantly having to go out to the disk and bring stuff from the disk into the memory. And so that mapping of the program and the data out on the disk into memory, that mapping is called virtual memory, right? And so we're gonna see how to do that mapping, and we want to understand that originally that was done because there was not enough memory available, and so you had to constantly bring in pages of memory from the disk. That's what they were called, pages. You had to bring them in from the disk into the amount of main memory that you had for the processor to talk to. And then the next thing to recognize is that that's not the situation we're in today. And yet virtual memory is more important today than it was back then. it's more important today, even though we have basically infinite amount of physical memory almost. We have DRAM and we can put down as much of it as we want, gigabytes and gigabytes of it. And so why is virtual memory more important today than it was, 30 years ago? And the reason is because we use this exact same concept of paging, of being able to page different sections of memory, of the memory that's out on the storage, the disk, using those pages and putting it into a small number of pages that we had in our actual hardware. We use that exact same principle, but now we use it as the foundation for security. So virtual memory is the foundation. It sits under security. This is the thing that allows us to have secure computing. And secure computing, what does that mean? Well, it's just from a real simple-minded point of view. That means that if I have a computer and that computer is running software that can look at your bank account information, that if there's some other software running on that same computer, that we have to make sure that software cannot look at your bank account information. So it allows us to have two completely different programs running on the same computer, and it allows us to keep the data from one from being looked at in any way by the other program. This is assuming that we're not a multiprocessor where the two things are sharing, working on the same task. We're talking about two programs that are doing completely different tasks. And the purpose of the second program could be to try to steal information from the first program. That could be the second program's purpose. And we have to prevent that from happening. Somehow we have to in no way can it ever happen that program can steal information from this other program. And so we see a bunch of words here that talks about how all this works. Programs share main memory. They share main memory, that's what we just said. But they each get a private virtual address space. And the way this protection happens is by the mapping. We're going to map the virtual space of programmer A, of user A. We're going to map it to a different physical space than all the program and data of user B. So it'll never overlap. So let's just draw a picture of that. So conceptually, we have the user A, user B, and he has basically infinite space. And over here, so this is virtual. And here we have the actual physical memory, of which there's plenty of it. There's a lot of it. But what we're going to do is we're going to say, okay, let's say that both these guys have this same part of their virtual memory. Let's say they're both using it, which is very likely. They're both going to start here from the bottom and start writing their program and allocating their data and all that stuff on the way up. It's very, very likely that these two sections that are at the same place will get used by both of them. Well, what happens is that when those pieces get mapped over here to physical memory, they're going to go to two different places. So there's going to be an actual mapping that moves them to two different places. And if B here tries to go here, he won't be allowed to do it. And if A here tries to go here, he won't be allowed to do it. And so that's the magic. How do you do that? How do you keep user B from accessing user A's physical memory space and vice versa? And the way we're going to do that is that we're going to have to check every time user B or user A generates a memory address. We are going to have to check to see whether that memory address is to a place that is mapped for him. And so while it's, while it looks like magic, if you look under the hood of this magic, it's really a bunch of transistors that are all doing work and, doing comparisons to check and see, is this reference okay? But before we get to the transistor portion of it, we want to talk about the operating system point of view. And so from the operating system point of view, these are pages. These are called pages. And they're the same size over here and over there, pages. And a page is equal to 4 kilobytes. That's how big a page is. That's how big a page has been for 40 years, since the dawn of time. Pages have been 4 kilobytes. And so when you go to the disk, so here's our disk out here. When you go to the disk, the minimum amount of stuff that you bring back from the disk is 4 kilobytes. And so pages are allocated in physical memory in 4 kilobyte pieces, because since you go out to the disk and you get 4 kilobytes, that 4 kilobytes is going to be associated with the user A or user B or user C. And so you're going to put all of that data into main memory, of course. So you're going to put it into physical main memory at the place where that page has been allocated. So even though user B thought that page was here and user A thought that page was here in virtual space, and those are the same, right? They're going to get mapped to do different places in physical memory. All right, so let's see a picture of how that works. So it's really, really simple. He says, okay, so we said the page is all the pages are 4 kilobytes. So that establishes that the bottom 12 bits here, bits 0 through 11, point to a byte within that page. So there's 4 kilobytes in there. So that part is not mapped. So you can see that this is not translated. Just goes straight through. So this is the virtual address. This is the physical address. See, the bottom 12 bits here are not translated. They just go straight through because that's the page. A page is owned by each user, and it's in a 4 kilobyte chunk. So you can, as long as you own that page, you can go anywhere within it, anywhere in those 4 kilobytes. So the part that has to be mapped or translated is the top part of the address. And so we're going to take that and we're going to map it to some other thing that points to somewhere else in physical memory. That this value here won't be equal to this value here. They're not equal. It will move it somewhere. And so, and in fact, again, for the same value here for two different users, you're going to get two different physical mappings. That's the whole point, is that you know, every time these match for two users, you're going to get, you know, a different physical mapping. Okay. And so the next thing we want to do is we want to look at a picture of how that's actually done, because it's quite important. He shows us it happening many times, but he never tells us what's going on. So first we want to get rid of a little jargon here, so we understand what this jargon means. So we have this jargon, it's called a high radix. What does high radix mean? So this is a low radix tree. Low, and in fact the radix here is 2, right? It's a binary tree, right? Splits 2 ways each time. It's a binary tree, right? And so what does a high radix tree mean? Well, a high radix tree means, well, it's not going to be binary, it's going to be some number bigger than 2. And in fact, we're going to use a high radix tree here where, quote, the radix, high radix tree, the radix, excuse me, the radix is equal to 10. So 2 to the 10th. And so a radix tree like that, right, looks like, you know, it looks like, you know, this. You know, and then each one of these is, again, you know, some huge number. It's really difficult to draw, but basically you're talking about, you know, how big the fan out is here, and we're talking about a big fan out. Okay, so what does that mean then? That means what we're going to do is we're going to take the address space, and we're just going to talk about a 32-bit address here. You can extend this to 64, but we'll just talk about 32. And so what we said is that our page size is 4K bytes. So again, that goes from 0 to 11, because 2 to the 12th is equal to 4K. And the bottom 2 bits here, right, are always the byte index. And so we have 4K byte pages. And the tree that we're going to produce, we're going to divide up the rest of the bits, which you know, up to bit 32. We're going to have 10 bits here and 10 bits here. So we have 10 plus 10 plus 12 is 32. That's good, because that's how many bits we have. And again, 2 to the 10th is equal to, you know, 1024. So our radix here, you know, is if, you know, conceptually it's 1,000, right? It's, you know, again, a binary 1,000, which is 1024. So we're dividing up the memory system. We're dividing up the memory system into 1024 4K byte pages. And then we're dividing that up into 1024 of these things, right? And so now what we want to know is, okay, how do we actually do this mapping now that we've said this is how we're going to separate it? So we need one more picture. And so now we're going to take that same picture. Let's see if we can get this right the first time. So we're going to take 10 bits here. And point that into our main memory somewhere, physical memory. And this thing here is called a page table entry. And again, this is pointing into main memory. So this is 32 bits wide. And the top bits are going to code what it's okay for this page to do, and which means, can you read it, can you write it, can you execute it? That's where all that kind of stuff is. It's here in this page table entry. But for our purposes, the thing that we care about that's in the page table entry is we need 22 bits, and we need 22 because we're going to point to somewhere a 1K byte region. And then we're going to take these 10 and point in here. So again, 10 bits here. And again, we'll have some coding which says what it's okay to do. And then finally, this all comes down. So again, this part here goes through unmapped. So 12 bits here just comes straight down. So 0 through 11 here, 0 through 11 here. And so this is our top 22 bits. And our physical memory here is 0 to 33. So we have a 34-bit physical memory. And this is a key point, that the virtual memory is only 32. This is only 32 bits, our standard virtual memory, but it can map to a physical memory that's bigger than that. That's perfectly okay to do. And that's why we have 22 bits here, because the size of this thing is 2 to the 34. The size of our physical memory space is not 2 to the 32, it's 2 to the 34. And so so to specify a particular entry, we need these 22 bits plus these 10 bits. So this gives us our mapping. So anytime that we need to create a mapping, we have to go through this access pattern. And so when we see the picture that the author has of the mapping, this is the mapping that happens in the top 20 bits. So it does it in a two table lookup. So it has to look up the first million, and then it has to look up the million 4K, right? So we have 1,000 and 1,000. So 1,000 and 1,000 is a million. And then finally we have down here 4K bytes, which is 1 4K bytes, which is equal to 1K word. And so we have 1K words, and then here we have 2 to the 10th 1K words, which is 1,000 of those. So 1,000 1K words, and then above it we have 1,000 of these 1,000. And so we go through this table walk to get to generate any mapping, a two level table walk. Okay. Now, so the author tells us, okay, well, when we have a page fault, that means, you know, when a user first says, okay, I need this piece of data, and that data is not there, he says, okay, we need to minimize how much that happens, because when we go out to disk, it takes millions of cycles. And okay, fine, that makes perfect sense. So we're going to just do the smartest thing that we can, which is pretty easy, because the operating system is doing this. And so the operating system can do it fully associative. It can use the best replacement algorithm. It'll do it because it has lots of time, and it'll save a lot of time every time you don't have to do this. And so this is the picture that we looked at. And then if we miss, we've got to go out to the disk and get it. So this shows the translation using the page table, except that it doesn't really illustrate, what has to happen. It just kind of shows it again the same way as before, without any additional extra information. So this is what we replaced, and showed that this actually happens with a two level table walk. That's how this really happens with that high radix table. High radix tree. Whoops, go away. Okay. There's nothing further helpful on here. It just, just shows more and more mapping. Okay, and we said we're going to use the best replacement we can. Okay, we're going to use LRU. And then the other thing we're going to do is we're going to use this thing called a reference bit. So this is really important when we're talking about paging, is that the way it keeps track of all this is it says, okay, I'm going to take a page that's stored out there in memory, and every once in a while I'm going to clear all the reference bits to 0. And then if some program references one of those pages out there in physical memory, then it will set it to 1. So every time it references a page, every time it goes and loads something, reads something from a page, it'll set that page table entry's reference bit to 1. It's also called he says it's called a use bit. So reference bit, use bit means the same thing. And then, okay, so then since he's cleared them, if he then needs to do replacement, he'll just look for pages that have the reference bit set to 0. And when he finds one that has its reference bit set to 0, he says, okay, that one is the one I could replace. And of course, you don't do this until you've run out of pages. Until you've allocated all your available physical pages, you won't replace any of them. But once you've filled out the memory space, filled out all of your physical memory with pages from users, then you're going to have to look and find one of them that has the reference bit equal to 0. And then finally, not only is there a reference bit, again, just like with the cache lines, we're going to have a dirty bit. Because if we're lucky, if a page that is going to get replaced isn't dirty, then you don't have to write it back out to the disk. And it's going to take millions of cycles to write a page back out to the disk. So we want to know if we have to do that. We don't want to do it unless we absolutely have to it. So we're going to keep this dirty bit. And if the page is not dirty, then we can just write over the top of it. Makes perfect sense. Okay, and then finally, we come to the transistor portion of this that says, well, all that stuff we just talked about, where, in our pipeline, here's our pipeline. It always comes down to we actually have to do this. If we do a load instruction, here we're going to actually reference the memory here in the MEMS cycle. Here we did the base plus offset during the ALU cycle. We did base plus offset to get the address. Remember this? That's where we take the base of the data structure and add the offset, add how far we're going to go into the data structure. We do that address calculation, and then we use that to access the memory. Well, this base plus offset, this is the user, this is the user's virtual address. User virtual address. And so, wow, this is a problem because we're going to have to access memory. Now, remember, our memory here is our data cache, or data cache. But our data cache is just a subset of main memory. And our main memory is physical memory. So the physical memory is the thing where we do the mapping. That's where we keep. It's that having different virtual addresses mapped to non-overlapping places in physical memory that allows us to keep two programs from touching each other's data. So this address calculation here by the program is a virtual address that he generated. And we know that the operating system is going to translate that. We looked at all the pictures of how it does it, a multi-level memory access to do that translation. But we know it has to be done, but we can't possibly, in this space of time, even conceptually, you can't do a multi-level page table lookup out in main memory. So here on the chip, we have to have this TLB, which is another cache. Another cache. And this cache holds these translations that we've been talking about. And so we have to take this virtual address that we generated here, this VA, and we have to use a cache inside the processor to basically immediately translate it to a physical address so that we can do this memory access. Now, without belaboring the point too much, the only thing we have going for us here is that the bottom 12 bits of the address don't have to be translated. So think about this for a second. If we arrange our cache to be in groups of 4K bytes, then we can actually do that memory access while we access the TLB to see if this is a valid virtual address. Is this user allowed to do this virtual to this physical translation? Is he allowed to go to this physical address? And again, this is the absolute fundamental way that security works on computers. We have to check every single virtual address that's generated by a user and make sure that he's not going somewhere where he can't go. This is the fundamental way that security works in computers. So you must do this perfectly correctly. However, at the same time, you've got to do it blazing fast, because if you don't, it's going to slow the processor down enormously. So we have to keep this cache. And this is where, and this is why all caches and processors are actually associative. We talked about this before, and why, gosh, it didn't seem to really increase the performance very much. But what associativity does is it allows us to arrange a cache that's bigger than 4K bytes. For example, 16K bytes, 4 times bigger. We can not have to translate the bottom 12 bits and go to all 4 sets, all 4 different sets of that cache at the same time. And while that's happening, because we didn't have to translate the bottom 12 bits for any of those 4 sets, at the same time that's happening, we can access our TLB and make sure that this reference that's being done by this virtual address by this user is okay. And that's what we do. So we make the caches multi-way set associative, allows us to access them with just the bottom 12 bits. And while we're doing that, we access this cache that's on the processor called the TLB. And then we bring those two things together and say, yes, here's the data I wanted, and is it okay or not? Is the guy allowed to look at this data or not? And so all this has to happen in that one cycle, the memory cycle here. Blazing fast has to happen. And this is the key to having our processor be fast and secure, is this translation. The translation fundamentally has to happen. And again, then the translation has to happen somehow on the CPU very, very fast. So multiple layers of tricks happening here. Another useless picture of the same thing. So this just says, okay, when you miss in the TLB, then that's when you have to go and hopefully that happens. We could just say must happen infrequently, because when you miss in the TLB, when you miss in that cache of the page table entries, when you miss in that thing on the CPU, then that's when everything is going to slow way down. You're going to take an exception. You're going to have to go out there and get a legitimate mapping for that guy and bring it in and load it in the TLB, and then you can start up. That's going to take a lot of time. So you got to make sure that your cache of your page table translation, it has to be big enough to make sure that happens very infrequently. So that's just what all this says. It says that, okay, every once in a while you're going to miss, and you've got to do it as you've got to refill your TLB with a new value and get going again as absolutely as fast as you can. For sure. More of the same. More of the same. And then we'll come back to this page. But before we talk about this page, we'll come back to this page next time. So before we talk about it, let's talk about, we got to go back now and address one more thing about hypervisor and the virtual machine monitor. And let's just talk about that one last thing here. So again, we've been talking about virtual memory. But before that, we talked about virtual machines. And virtual memory, remember, this is all about security. How do we make our computer secure? Virtual machines, this is all about, convenience. And convenience, again, remember the thing that was convenient is that we said that we could have, app plus OS, app 1 plus OS, app 2 plus OS 2, app 1 plus OS 1, app 2 plus app 3 plus OS 3. 3 different operating systems, 3 different applications. We're going to run them all on top of this. I'm going to call it hypervisor, since that's the generic term. And then that's going to be on top of the hardware. Now, remember once we compile the app plus the OS together, that this is now a user. These are now user programs. That remember this OS thing here, this thing that used to have the privilege to do stuff, doesn't have privilege to do anything anymore. And so that's really key to what we just talked about in virtual memory, because remember OS1, OS2, OS3, which again can be completely different operating systems doing, completely different things. They think they are in charge of the virtual to physical map. But they can't be anymore, because we have 3 completely different operating systems running now on top of this one piece of hardware that only has one piece of physical memory, one piece of main memory. And so we have to keep, all 3 of these guys here that all think that they are in charge of the mapping. We have to, relieve them of that view, because they would be mapping everything all on top of each other, right? It's not, if there was only one OS on top of the hypervisor, you could imagine that he would be doing things consistently. But we have 3 different applications and 3 different operating systems all running up here on top of this hypervisor. That means that he must intercept all VA to PA done by these guys. And the hypervisor, is the only guy that can do a VA to PA. So these guys, so every time this app plus OS3 wants to, bring in a new page, this guy, the hypervisor, has to intercept that and do his own mapping. So this guy goes through his mapping table, and then this guy here has to go through his mapping table to move it somewhere else. So you can imagine that this is extremely burdensome from a time and software point of view. And so now what has to happen in the CPU is that our friend there, the TLB, the cache, has to now be able to map the translations for 3 or n. This is 3 is just an example here, for n different app plus OSs must be translated in the CPU, in the TLB, in the TLB. Otherwise, it'll be, ridiculously slow. This whole system would never work if the TLB, couldn't do these now multi levels, right? Before we had, a 3-level lookup. Now each of those, excuse me, a 2-level lookup, each of those 2 levels would have, multiple levels, lookup done inside of those. So the number of levels of lookup, stacks up, for every layer that we put on this thing. And so that's how virtual memory and virtual machines end up having to be talked about at the same time, because the most important thing that virtual memory does is this memory translation for security. And when you put a virtual machine in the way here, you've got to do that translation for every different OS and app that you've loaded on top of your hypervisor. And so this is the really hard problem. You've got to still maintain security and get this flexibility of being able to put all these different applications and OSs on top of this same piece of hardware. So this is, you know, staggeringly difficult and complicated to do. But this is the real world. This is what it really matters. This is what it really means to support a virtual machine, is that to support a virtual machine, you've got to support virtual memory. You got to do those two things at the same time. And that's where the rubber hits the road, is making those two things work together. All right, so we're done. We will pick this up next time.